This video will focus on programming in the real logic programming languages, Prolog, an older language, and Mercury, a newer one. So this is Prolog code, and the definition is fairly similar to the generic factorial definition we saw in the previous video, but it has a few small changes that are necessary to make it work in Prolog. We still have a base case where we say the factorial of 0 is 1. We end every horn clause with a period. And then we have a recursive case where we say the factorial of n is some answer. This colon dash is meant to look like a backwards pointing arrow. So we're saying that this is implied by the body of the predicate, which is defined here. And then the comma represents the logical and. So this predicate factorial is satisfied if all of these facts are true. So we confirm that n is greater than 0, and then we introduce a new variable named next that is n minus 1. Now, in the more generic syntax that we used in the previous video, we didn't define this extra variable, and we also didn't define this extra variable answer either. But Prolog needs this because it's very flexible with its variables. Any variable could be thought of as either an in-mode parameter or an out-mode parameter. And I'll elaborate more on what that means in a moment when talking about Mercury. But for now, just know that Prolog doesn't really let you effectively put sub-expressions where variables should be. There are some cases where it's syntactically allowed, but usually to make the code work, you're going to have separate variables. And then, as we have here, we say that next, a totally new variable, is defined to equal n minus 1. So when we say factorial next, we're really saying factorial of n minus 1, and the factorial of that is some new variable named partial. And our final answer, which is up at the top here, is defined down here to be n times partial. Now, some important things to note here are that all variable names have to start with capital letters. That's the n, next, and answer. And that predicate names like factorial have to start with lowercase letters. So let's test this out using the SWI Prolog interpreter. So Prolog has an interactive interpreter, and I can load this file into it like so. And now I can do queries on predicates that are defined in this file. So I can say factorial 0, 1. I can check if it agrees that's correct, and it simply says true. And then, more usefully, I can say that the factorial of 5 is some value, has to be a capital letter on that variable name. And so this is a query where I'm asking, is this satisfiable? And if so, what will value be? So I press enter, and it returns that value is 120, and that's correct. The factorial of 5 is 120. Now you notice that I still have a cursor here, and what I press at this point is important, because a useful feature of Prolog and logic programming languages in general is that they can find multiple satisfying assignments if that's appropriate for the given problem. Now for factorial, there's only one answer, but the way I've written this code makes Prolog think that it's at least possible that there's another answer. And before, when I got this true result, I pressed enter and it just stopped computing. If I press space instead, it says false. The reason for that is that it finds a satisfying assignment of value equal to 120. And if I press space, it will attempt to find other satisfying assignments, but fail to do so. So that's why it gives up and says false. So I did successfully compute the factorial. It's just there's only one factorial, not more than one. I could actually change this definition to be a bit more strict and to be aware of that. So the reason that it at least entertains the possibility of there being another answer is that I have these two cases. Once the recursion reaches the base case where the first parameter is 0, clearly the base case of these two cases applies, because if the first parameter is 0, the second parameter is 1. But Prolog will also check the second case, because the pattern simply shows that there's a parameter in and a parameter answer. So it will plug the 0 into here as well. It is only when it realizes that 0 is not greater than 0 that it will fail. But it has to actually check that case. So it's exploring two possible options at the final step, which is why it doesn't know in advance that there's only one answer. But we can write code that functions the same way in a slightly different manner to make sure that Prolog knows there's only one answer and give that one right away. To modify this code, we're going to avoid having two separate cases. We're going to have only one case where we have factorial of n and our answer, but now we have to check within this case if n is equal to 0. So there is a conditional statement in Prolog. First, I have to check for n equal to 0. And then the conditional structure in Prolog is a bit unusual. We say that if n is equal to 0, then that implies, so I have a dash and a greater than sign, so it looks like an arrow. And so that implies that we're in a base case. So if n is 0, then I want the answer to be 1. Else, I will use this semicolon to indicate the alternative case. And so in this case, I have my n greater than 0, my next is n minus 1, my factorial, and my answer being that. Let's test this out. Exit the interpreter with halt, and then go back in, load it again. I'll run factorial 5 value. It works. And also, it didn't have a cursor waiting for extra answers. It just gave me one answer and exited immediately. So if I ask it what the factorial of 5 is, it'll say it's 120. If I simply ask it, is the factorial of 5 120, it says true. If I ask it if the factorial of 5 is 100, it says false right away. Okay, so all useful facts, and I can plug in different values here. I can do the factorial of 7, and I don't have to name the variable value. I can call it just a. It'll say a is 5040. But what happens if I put in a negative value? It says false. So that's good. What I'm going to do now is take this over to Mercury and show how it is similar and different. So now I have Prolog code on the left and Mercury code on the right. And as you can see, it's very similar. I have factorial n of the answer. If n is equal to 0, I only have one equals here. That implies that answer equals 1. I don't say is. Otherwise, as long as n is greater than 0 and factorial of n minus 1 is partial, then the answer equals n times partial. And then here, I can actually have the n minus 1 in the predicate call. Mercury is a compiled language, so I don't have a nice interactive interpreter. And I actually have to have some other code up here. This is a main predicate that supports the code below. So this code calls factorial, says, what is the factorial of 5? Gets an answer. And assuming that that works, it prints out the answer. Otherwise, it says true, which means that the predicate will succeed but print nothing. And so there's a bit extra infrastructure needed. I also have to import some basic things like integer list string. I have to define a signature for the main predicate and name my module. So this is all extra stuff that makes Mercury a bit more daunting at first, but it's in place so that you can have faster compiled programs. So we'll ignore that for now and just focus on this definition and the fact that I'm going to print out this message here. And so when I compile and run this code, so this is the compile command, it works, I run it, and it says the factorial of 5 is 120. So these both work, but why are there differences? So let me first point out that Prolog is a little bit flexible, but in ways that make it a bit complicated. So here I'm using this word is, and that's sort of like an assignment operator in Prolog. It's not quite accurate to say that, but whenever you say is, it's assuming that the left-hand side is a variable that hasn't received a value yet, and the right-hand side is some sort of expression. Now, if I replace this with a single equals, and also this one and this one, so every time it's used, I do that, and I load this up, I can still run this code, say factorial 7 of a, but now it fails. And same thing with this. I mean, that should fail, but factorial 5 of some value, run it, fails. So Prolog has an equal operator. It has an is operator. It has a separate equal operator. But in Prolog, all of these things mean slightly different things. And that can be a bit complicated and difficult to understand. In Mercury, it simplifies things a bit. There's just the equals. And so in that sense, it's kinder to beginners. But there's some other ways in which it's more challenging for beginners, which I'll explain in a moment. So I'm going to fix this Prolog code and go back to using is. Now, the other weird difference with the Prolog code is that I have to define next as a variable, and I have to define, answer is defined as a variable in both of these, but next is the weird one, because why can't I just put in -1 here? And let me show you what happens if I do. So comment out that line. Once again, fails. So I really do need to have the Prolog code look like this in order to get the appropriate behavior that I was getting before. So why is Mercury more flexible in this regard? Well, I say Mercury is more flexible. It's actually more strict, because there's this extra line of code before the predicate definition that says factorial is a predicate, and it has two parameters. The types of those parameters are int and int. So Mercury is strictly typed. It is strongly typed. And I also have to define the modes of the variables. So what I'm saying is that the first parameter is an in mode parameter, meaning that when I call this predicate, I have to provide a concrete value for that. And that's what all my examples have looked like. Even when I'm using the Prolog code, I've provided the value of 5, and then I've had the other parameter be undefined. And so that is what it means for it to be an out mode parameter. So an out mode parameter is one that can be provided by the code. It's one that can be computed. It's also allowed to put in a specific value there, and in that case, the code will simply determine whether it's correct or not. But by saying that I have this parameter coming in, that means it is allowable for me to simply define an expression when I call it, because I don't need to remember the name of that variable, because there's never going to be a result coming back out of it that'll need to save that value. So that's the flexibility there. Now, this last bit of code is saying that this is a semi-deterministic predicate. Why is it semi-deterministic? So deterministic would mean that every time I call this predicate, there's only one correct answer, and that the predicate always succeeds. Semi-deterministic means that if I get an answer, it'll always be the same answer. And that's true, because the factorial of n is going to be the same value no matter what. But it's semi-deterministic because this predicate could fail. How could this predicate fail? Well, it'll fail if n is a negative number. Because if I ask it what the factorial of -5 is, that's not going to satisfy this check that n is equal to 0, but it's also going to fail this check that n is greater than 0. And so this is the reason that in my testing code above, I have to say if factorial of 5 has an answer, basically, then I can print it out. So how can I get around that? So I'm going to make this predicate be purely deterministic by adding a check for this n greater than 0. So rather than simply requiring it to be true and moving forward, I'm going to do another implication. So if it is greater than 0, then I can do those two steps as before. But otherwise, another else case, I'm going to have an error. I'm now covering every case. So if n is 0, the answer is 1. If n is greater than 0, then I have this recursively computed result. Otherwise, I have an error. Now, an error is not the same as failing. If I were to put a fail here, then this would still be semi-deterministic, because when a predicate explicitly fails, that is handled differently than if you have an error. Having an error will halt the execution, or possibly pass something up to be handled elsewhere, but it's still considered a deterministic outcome. So I have a deterministic predicate now, and I've also already modified the main predicate above to remove that conditional structure, because now that Mercury knows that factorial is deterministic, it feels fine with me defining the code in this way without those if statements. So I can compile and run this code, and it works just fine. Now, in my previous definition of the main predicate, I had the words if then else. And that's just another nice thing that Mercury offers. So both Prolog and Mercury have this kind of weird arrow, semicolon, if then else structure. But only in Mercury is it possible to simply replace that with a much nicer looking if n is equal to 0, then answer is 1, else we do this computation. So, and then another if statement here, so it's nested. If n is greater than 0, then we have these. Else we have that. That compiles. And we run it, and it works just fine. Now, it's common to also put some parentheses around this to make it a bit more organized, but clearly the code compiles and runs fine without that. So I'll just leave it as it is. Now I'm going to share one more example in each language, and the solution is actually the same, because both Prolog and Mercury have a built-in predicate called append that combines two lists into a new list. And we're going to use the append predicate to define rev, which is for reverse. So we are reversing a list of elements. And they use the same list syntax. In many ways, Mercury is built to simply be a strictly typed compiled version of Prolog. So there's a lot of syntactical similarities there. And both languages have pattern matching for lists, which is nice. So we see that in the Prolog version, we're saying that the reverse of an empty list is another empty list, and that is a headless horn clause. It's a base case. And we have another case where we say that X is the head of a list and XS is the tail of that list, and they're separated by this vertical bar. So we have a list that has at least one element, which is the head. And if that is the case, then we can reverse the tail of the list to get a new list, Ys, of the reversed elements. And if we append that reversed list to what we call a singleton list, so a list of one element, a singleton list of just X, that'll give us the result, which is a reversed list. And we can test that out in Prolog interpreter. Say rev 1, 2, 3, 4, 5, and the result of that will be 5, 4, 3, 2, 1. And that is deterministic. Notice that I go straight to a new prompt because it has no doubts about there being other answers. That's because the pattern here is exhaustive. Here, a list is either empty or not empty, and so that's exhaustive. And that's also good enough for Mercury. So in the Mercury version, I don't need to have an if-else structure. I simply have a case where the lists are empty, a case where it's not, and I have to indicate that the first list is an in parameter and the second list is an out mode parameter. And in that case, I get a deterministic result. So I can compile this, run it, and I have some code in a main predicate here that defines the list 1, 2, 3, 4, 5, does the reverse of it, and then prints out that the reverse of that list is this reversed list. However, I don't want to leave you with these definitions because although they're conceptually easy to understand, these are considered somewhat inefficient implementations of the reverse operation. These are actually O of n squared because we're doing this O of n append operation at every step. There's a better way to do the reverse that's only O of n. It requires a helper predicate. So I'll define that version. So we see once again that the code is essentially the same in both languages. In Prolog, we have reverse A of B is the result of calling this helper predicate, where we have an initial empty list in the second slot. The idea being that this empty list will accumulate the reversed result. So in the base case, once the first list empties out, then the second list is the final result, and that simply becomes B, the final result, which is here also the final result. In the recursive steps of this helper predicate, our first list is not empty yet, so we cons the head of that list to our list that is accumulating elements in the reverse order. Notice that R stays the same. The reason for that is that in this base case where X is X here, so the second and third parameters are the same, we'll unwind all the recursive calls and we'll sort of simply return these R values up the recursive call chain to get to our initial result. And so we can confirm that this works by running it in the interpreter. Reverse of 1, 2, 3, 4, 5 is indeed 5, 4, 3, 2, 1. So that works. And the code for Mercury is the same, except we have to define the type signature and the parameter modes. So the first and second parameters are in mode lists of some generic type T, and the third parameter is an out mode list. So it is essentially the result. And overall, that is a deterministic predicate. And I have the same test code from before, so I can compile this, run it, and it says that the reverse of 1, 2, 3, 4, 5 is 5, 4, 3, 2, 1, which is exactly what we would expect from this main predicate defined there. So that's a nice little introduction to both Prolog and Mercury. It definitely requires you to think in a slightly different manner because you have your results being parameters rather than a separate returned value. But from the examples I've shown you so far, we're not really doing anything radically different from what we might do in other languages. We're using a heavy emphasis on recursion. We have pattern matching, but we're essentially still providing inputs and getting outputs. So this style is similar to functional programming in a sense. But in the next video, I will show off some of the true strengths of logic programming, specifically how they are able to find multiple answers to a problem due to the flexibility in how predicates can be defined.